Good morning, everybody. Today we're going to talk about Chapter 5, which is about the aqueous solubility of chemicals. So aqueous solubility is the equilibrium partitioning of a compound between its pure phase and water. And remember our diagram of the world. This was our highly oversimplified map of the world, right? And previously we talked about, the first thing we talked about was the pure phase partitioning into air, which was vapor pressure. Right? That's where we started. And the reason we started there is because you can assume ideal behavior in the pure liquid phase or solid phase. And you can pretty much assume ideal behavior in the gas phase because we have the ideal gas law. Gases generally obey the ideal gas law. And so you can assume ideal behavior in both phases. And as a result, the only thing that really matters in air is the temperature and the pressure. So that was a good place to start. Now we're going to up the level of complexity by considering the pure phase, which again will be displaying ideal behavior. And now we're going to look at the partitioning of the pure phase into water. And so this is going to up the level of complexity because water is definitely not ideal. Chemicals do not behave in ideal ways when they're dissolved in water. So that's the first thing. The second thing is there's all different kinds of water. There's fresh water. We might go out to the boat dock here in New Brunswick in the Raritan River. At that point of the Raritan River, it's fresh. It has almost zero salinity. But then if we go a little bit further downstream, the salinity will start to increase. We get out to Raritan Bay, and the salinity is suddenly about 0.3 molar. And then when you get out to the open ocean, salinity of the open ocean is about 0.5 molar. So we can have a whole range of salinities. We can also have different kinds of water. We have surface water, we have groundwater, we have pore water, which is the water in between the little spaces, the little grains of sand or dirt that are making up the soil. We can have fog water, we can have rainwater. So we have all different kinds of water, and they all can have slightly different properties depending on what things are dissolved in them. So when we're talking about water, we got to worry about temperature. Yes, always have to worry about temperature. We also have to worry a lot about salinity. And we're going to spend a little bit of time in this lecture talking about co-solvents. Co-solvents are other chemicals that are dissolved in the water that change the properties of the water. So the most common co-solvent system that you might be familiar with is beer, right? Beer is about 6% ethanol in water. And that 6% ethanol really changes the properties of that water system. So it behaves differently with respect to how it dissolves organic contaminants. So we're going to spend some time today talking about this. This is the aqueous solubility of your compound in water. Why do we care about water? Well, obviously water covers 70% of the Earth's surface and it's constantly in motion. Or most water is. I suppose Passion Puddle's not doing much, but most water is in constant motion. And this is why it becomes an important vehicle for transporting chemicals throughout the environment. So the two main pathways for chemical transport are atmospheric transport and water transport. Atmospheric transport, of course, is going to be very important for chemicals that have a high vapor pressure and can get into the atmosphere. But for chemicals that have a very low vapor pressure, they don't really go anywhere in the air. So the main way that they get transported around is in the water. And solubility is important for us to discuss because it is important in its own right. It's important to know what is the maximum amount of my chemical that I can dissolve in water. But it's also important because it's going to lead us eventually to talking about our friends, the octanol water partition coefficient, KOW, and the air water partition coefficient, KAW, which is also called Henry's law. I like this table. This is a table from the first edition of the textbook. You guys have the second edition, and for some reason they got rid of this table, but I like it because it shows sort of the range of solubilities that you can expect from common organic chemicals in the environment. So here you got dichloromethane, right? It's got a very high aqueous solubility here of almost 1 mole per liter. So this is your CWSAT, which is water solubility, and the units here are moles per liter. So dichloromethane, very high solubility. Add a couple extra chlorines on here. This is tetrachloroethylene or perchloroethylene, which is also called PCE. So PCE, now you've added a couple of extra chlorines and a carbon, and now the solubility is down to about 10 to the minus third mole per liter. Alkyl benzenes down here have a range of solubilities from the smallest, benzene, over here down to something with a long alkyl chain on it. And so we have a range of maybe, 3 orders of magnitude here in the solubilities of the alkyl benzenes. You add a chlorine onto that benzene and suddenly that drops the solubility, maybe half an order of magnitude or an order of magnitude. And when you keep adding more chlorines over here, your solubility goes way down, right? So the more chlorines you have, the lower the solubility. That's because the molecule gets bigger. Chlorines are generally pretty large as atoms go, so they make the molecule bigger, and bigger molecules have lower solubilities. So that's what's going on here with PCBs. You add a whole bunch of chlorines over here onto this decachloro PCB, also known as PCB209. And now you've taken your solubility way down to about 10 to the minus 11 moles per liter. The phthalates over here also have benzene rings on them, right? But then they've got this other thing on here, which is much more polar, right? So this is polar, and this whole functional group over here with the carbons and the oxygens is also hydrogen bonding. It'll accept hydrogen bonds. And so this is going to make it much more soluble. So compared to benzene over here, this phthalate is a good bit more soluble, maybe an order of magnitude more soluble. But as these side chains here and here get longer, here and here, the solubility will go down. Similar here for PAHs. Here's naphthalene, only 2 rings, got a solubility around 10 to the minus 4 moles per liter. As you get bigger and bigger, this thing has 5 rings, and it's got a much lower solubility, around 10 to the minus 10. So that's a quite low solubility. Same idea here for aliphatic hydrocarbons. As you add more carbons, the solubility goes down. So we're looking at an overall range of about 12 orders of magnitude here in aqueous solubility across the kind of chemicals that we think are important in the environment. Okay, so this is where we have to show you some ugly math with lots of freaky symbols. And the textbook that we're using, the Environmental Organic Chemistry textbook, was written mostly by René Schwarzenbach and Phil Geschwend, and also Dieter Imboden. And they really love this concept of activity coefficient. Activity coefficient, and that is this thing here, gamma. Okay, so gamma is describing the extent to which the behavior of the chemical is no longer ideal when it is dissolved in water. So it's describing all the things basically that have gone wrong. Why is the chemical no longer happy? Why is its intermolecular forces now much less favorable than they were when it was in its pure liquid phase? So if we consider an organic liquid that's dissolving in water, we have the chemical potential of the organic liquid itself over here. So this is your compound I when it's in its pure liquid form. And that is equal to its chemical potential of I in the pure liquid form when it's at its reference state. So the star here means we're at the reference state. Plus this correction factor, RT, natural log of the activity coefficient multiplied by the mole fraction concentration of the chemical. Okay? Now, you might be saying, well, wait a minute, the mole fraction concentration of the chemical when it's just a pure chemical is 1. And you'd be absolutely right. And the activity coefficient of the chemical when it's in its pure liquid phase is about 1. And you'd be absolutely right there too. So the natural log of 1 times 1 is 0, and this whole term right here collapses to 0. But when we start talking about the chemical potential of your little chemical I in the aqueous solution now, it is again equal to the chemical potential of the pure liquid form at the reference state, right? Plus the same correction factor, only now it's the activity coefficient of your chemical in water times its mole fraction concentration in water. And those are not going to be 1. Some of you may have taken aquatic chemistry where you calculated activity coefficients for ions. Like you might calculate an activity coefficient for sodium or for iron 3. And when you did that, you used things like the Debye-Huckel equation, and you got numbers usually less than 1. For organic chemicals here in this class, when we calculate activity coefficients, they're going to come out to be a lot greater than 1. In many cases, they're going to be pretty huge. Okay, so we have our chemical potential of the pure liquid, we have our chemical potential of our chemical dissolved in water. At equilibrium, these chemical potentials are equal, right? So if you subtract one from the other, you get 0. Delta G is 0. And so these two terms cancel out when you're subtracting one from the other. Those are canceling out. So what's left here is the difference between the activity coefficients and the mole fraction concentrations of the chemical. And we could take this equation here and we could rearrange it so that we get now the ratio of the solubility of the compound in water divided by its mole fraction concentration in the pure liquid phase, and that would be equal to this nasty beast over here. And notice that since we're at equilibrium, we are at saturation with respect to this organic chemical, so we put the little sat up there, and we put it right here too. Here I'm just repeating the equation that we had before, and we're saying, okay, yeah, we do know that the mole fraction concentration of the chemical in its pure liquid phase is 1, and the activity coefficient of the compound in its pure liquid phase is 1. So those parts of the equation sort of collapse and disappear. And now we're left with this, the natural log of the mole fraction solubility is equal to RT natural log of the activity coefficient of the compound in water at saturation. And we know that that's also going to be equal to the delta G of the reaction, delta G over RT. That's why we don't cancel out the RTs over here. We leave them because we need an RT over here. Okay, so what it's telling us is that the mole fraction solubility of the compound in water is equal to the inverse of its activity coefficient, right? So if the activity coefficient is huge, the solubility is small, and vice versa. Now, no one in the real world uses mole fraction concentration units. They're silly. No one would bother. What we actually use usually is molar units, or sometimes we use milligrams per liter. But let's say we're going to use molar units. In order to convert the mole fraction solubility over here into molar units, we need a conversion factor, and that's this thing here, this V bar W. This is the molar volume of the water. Okay, that's what we use to convert, just to convert units so that we can be talking in moles per unit, moles per liter units. Makes much more sense. So that was all for liquids. For solids, we have to account for the fact that you need to melt the solid first to get it to dissolve in the water. Okay, so you need some additional energy to melt the solid before it can dissolve. And so the aqueous solubility of the compound, if it was a liquid, is equal to the solubility of the compound when it's a solid multiplied by this term, which has to do with the delta G of fusion, right? The delta G, the free energy required to melt the solid. And we know from the vapor pressure lecture that delta G of fusion could also be expressed as the ratio between the vapor pressure of the liquid and the vapor pressure of the solid here. And so we can calculate the solubility of a solid if we know the solubility of the equivalent liquid by just using this ratio of vapor pressures, right? So that becomes an easy way to convert back and forth between the solubility of the solid and the solubility of the liquid. And there's a couple of helpful equations over here to remind you. So here we have the activity coefficient of your compound in water at saturation, and it would be, again, the inverse of the solubility here with the molar volume of water here used as a correction factor. And then because we're talking about a solid, we need delta G of fusion over here. So you could calculate the activity coefficient of the compound, which is a solid at room temperature or at whatever temperature you're working with, using this equation. And over here, if you want to use this equation to calculate the solubility of the solid from the liquid or the liquid from the solid, you need to know the ratio of the vapor pressures. And remember, we had an equation for doing that in the vapor pressure lecture that relied on the delta S of fusion at the melting point. This does not mean multiplied by the melting point. It just means at the melting point. Okay, people often get confused by that. That parentheses TM there does not mean you multiply by the melting point. So why do we bother with this whole concept of the solubility of a compound that is a solid, but we talk about it as though it's a liquid? Why do we do that? That's crazy. It's confusing. And every year I always ask you on the midterm to explain this concept to me, and no one can ever do it. But the reason that we do it is because there's very clear relationships between things like the total surface area of the compound, this is in square angstroms, and its enthalpy of dissolution, the amount of energy required to dissolve it in water, right? There's a clear relationship here. There's a linear regression here. It runs very well through all of these points. These points are the solubility of the hypothetical subcooled liquid. Remember, we talked about that in the vapor pressure lecture. Now it rears its ugly head again. We're talking about the solubility of the hypothetical liquid. And the reason we do that is because if you plot that as, total surface area of the chemical versus the delta H of the hypothetical liquid, you get a nice straight line here. And you can, use this line to predict the delta H of other compounds that are maybe for which you don't know delta H, but you can easily calculate their surface area from some kind of computational chemistry program. So that works great, and that's why you do it. But if you tried to do it using the solubility of the solid, the delta H required to dissolve the solid, those points are way up here. And clearly they don't fall on a line. And benzene, for example, down here is not a solid, so we don't have an equivalent point up here for benzene because it's not a solid. So you'd be trying to draw a line between all of these crazy points and you'd throw up your hands and go home and quit. So that's why we spend our time talking about the solubility of the hypothetical subcooled liquid. Here's a similar situation over here. Again, total surface area is plotted versus the delta H, and you get a nice linear correlation for a whole series of alcohols. So that's why we bother with the hypothetical liquid, because it's relatively easy to predict how hypothetical and real liquids behave, but it's very difficult to predict how solids behave. And the reason is that the delta H of fusion is really tough to predict. Remember, we talked about this in the vapor pressure lecture, that the amount of energy required to melt a solid is tough to predict because every solid has a very different crystal structure. And even a small change in the structure of the chemical can introduce a big change in the crystal structure of the solid. So that's why we bother with the hypothetical subcooled liquid. And another reason why we bother is because the melting points of these compounds can be quite difficult to predict, but the boiling points are relatively easy. So here's an example of that. These are a whole bunch of different PAH molecules, right? You can see that they're increasing in molecular weight. The melting points, though, are bouncing around, up, down, all over the place. Okay, but the boiling points are increasing in a nice linear fashion. And so here's the regression for the molecular weight versus the boiling point right here. So this is for TB. And you can see that the R squared here is 0.95. You get a really strong correlation between boiling point and molecular weight. But down here, this is the regression for melting point. And the regression is not nearly so good. The R squared is only 0.3. So again, predicting the melting point is very difficult. Predicting the boiling point is pretty easy, which is another way of saying that the delta H of vaporization is easy to predict, but the delta H of melting, the delta H of fusion, is much more difficult. And finally, we've talked about liquids, we talked about solids. Now we need to talk about gases. So the solubility of gases is tricky. How do you report the solubility of gases? What is the concentration of the gas in its pure gas phase? So the way we do that is we express the solubility of a gas in terms of what happens when the gas is present at 1 atmosphere, which is the same thing, or close to the same thing as 1 bar. So that's the common approach. We do that for gases like freons, which we're going to use as an example in one of our homework problems. Methane, stuff like that. We express the solubility at 1 atmosphere. Oxygen, of course, is an exception. The concentration of oxygen in the atmosphere is 21%, and that's pretty constant. So we express the solubility of oxygen at 21%, or 0.21 atmospheres. And it's a useful thing to keep in the back of your head that just as a rough approximation, the solubility of oxygen in water, of course, it's temperature dependent, but under a lot of circumstances, it's somewhere around 10 milligrams per liter. And that's a useful number to keep in the back of your head. Okay, so for gases, so for solids, we had a phase change cost. We had to input energy to melt the solid before we could dissolve it in water. For gases, we have a phase change advantage. It's not a cost, it's money, it's energy that we get back by condensing the gas to a liquid. All that energy that it took to turn it into a gas in the first place, we get back when we condense it into a liquid. And so we get a phase change advantage. So the solubility of the hypothetical superheated liquid is what we're talking about now because it's a gas, so it's a superheated liquid. And you can calculate that from maybe an estimation technique like the ones we just saw, which use total surface area to predict solubility. So you might predict the solubility of the liquid, but then you might need to convert it into the solubility of the gas. And to do that, you would multiply by this correction factor. Here's the theoretical partial pressure of the gas at that temperature that you've been given. which might be greater than 1 atmosphere. It's the partial pressure of the gas at that temperature, and since that temperature is above the boiling point, the partial pressure of the gas is going to be greater than 1 atmosphere. It's like we're on Jupiter, could be 3 atmospheres, could be 10. And then here is the actual partial pressure of the gas in your system. So if you're talking about methane, for example, the theoretical partial pressure of methane is going to be several atmospheres up here, right? But the actual partial pressure of methane in the atmosphere is really, really low. It's in the parts per billion or maybe even parts per trillion range. So there'd be a big ratio here.